So our next speaker would be, yes, Professor Debbah. Are you there?
Yes, I'm there.
Brilliant. Okay, thank you. I can see your slides as well. That's great. So Professor Debbah is a IEEE Fellow, WWRI Fellow, and EuroSAPE Fellow. Also, Institute Louis Bachelier Fellow. He's Vice President of the Huawei France Research Center, Director of the Language, Mathematical and Computing Research Center, Joint Director of the Mathematics and Algorithmic Science Lab. So the title would be Mobile AI, Challenges and Opportunities. So Professor Debbah, the floor is yours.
Okay, thank you very much. You hear me well? You hear me?
Yeah, we can hear you really well. Thank you.
So thank you for the opportunity. So my talk is going to be more or less about presenting the opportunities that we have today on using AI for the telecommunication industry. So as far as I'm concerned, I'm working for TII, which is the Technology Innovation Institute, which is in Abu Dhabi, and working on the topics of fundamental AI, telecommunication, and also cybersecurity. I'll be talking about three things. First, doing an overall introduction about the topic, and then using AI for building networks at the moment, and networks for making AI, or what I call distributed AI, happen. So the main reason that AI has been kicking in the industry of telecommunication is the transition from what we call generation of communication. I think you're all familiar with 2G, which was mostly intended for what we call mobile for voice, and which was issued in the 1990s. Then 3G came in 2000 with a target of providing mobility for data. 4G came in, and as you all know, you have the ability to browse on your internet, and that's what we call mobile for internet, and that's what 4G brings in. 5G, which is now massively deployed in big parts of the world, was mostly intended for what we call the Internet of Things, and the goal was to provide mobility for all these things. As of today, we're building a whole framework related to what we call 6G, and in which basically the whole idea is to provide the connectivity in being able to connect the different intelligence. What we bring that is that, as you all know, a lot of the AI that has been very cloudified and very put into a centralized server, now there's a lot of devices which have what we call embedded AI. This is in the realm called edge AI. And one of the big questions is how to build basically the kind of network which connects the different models that we're building in order to build collective intelligence out of this massive individual intelligence. Of course, the topics which are related to federated learning, distributed AI, multi-agent distributed reinforcement learning are part of the things that we're trying to build here for 6G, on which we want to leverage and build this super distributed computer, which will enable to connect nearly every part of our network where you have deep neural network which are installed. Within the field of communication, learning by itself is not new. As you all know, signal processing has been at the heart of basically a lot of control and learning. And the idea of VNR, as you all know, was exactly what we use today in wireless, is that you try to define something what we call quality of service. In general, it's the kind of rate that you have. In general, the kind of environment on which you want to input your data, you do not know it, and you will learn it through what we call a process called feedback. Feedback in general in systems of communication are sending back from the receiver to the transmitter what we call an ACK, an acknowledgement or non-acknowledgement. And based on that, you take a new decision on which you can work. And people in our community have been using for many years learning algorithms. Here you have a list of algorithms which have been used and showcasing also the convergence of these algorithms. And in general, these algorithms have different features, and depending on the kind of utility function that you want to maximize, well, basically you can showcase a lot of results which are quite interesting. And in general, when you're not able to showcase convergence, what you try to do basically is to try to convexify your function. Because in these mechanisms, we know that when the function is convex, it has right properties. And how we convexify in communication is just by taking what we call the mean rate, the mean beta rate, some kind of mean metric which convexifies your function. And in this case, basically you have the right properties. It turns out that all these learning mechanisms have not been put into place in networks. And today, of course, with AI, things are changing. The main reason this shift is happening is that when you start learning in a classical setting without the deep aspect, you have a problem of what we call exploration versus exploitation trade-off. It takes time to learn. In the dynamics of wireless, especially, where people are moving, by the time you learn the different properties of your network and you're able to converge, it's already too late. Users have been out of the network. There's a lot of changes in terms of requests that happen. Of course, today things are changing because when you start adding some kind of deep insight in the sense of gathering and building a model based on the past, then you can showcase that the convergence rates are much faster and you can build up basically networks based on these ideas. The second thing, of course, is not using AI to improve network, but using basically AI for networks. Okay, this is also not new in communication. There's a famous paper of Shannon called "Programming a Computer for Playing Chess," and in that paper, of course, Shannon, out of his two fundamental papers that you all know, one on cryptography and the other on information theory, proposed, of course, the ideas of using machines for doing communication. And these goes for machines for designing filters and equalizers, that you can design on-the-shelf filters and equalizers, to things which are more advanced, like routing protocols, to things also in terms of doing strategic decisions. And of course, if you read that paper, he expresses, with the example of chess, that the computing power that we had at that time was not enabling us to fulfill all these 8 requirements that we're talking about. And I think you're all familiar with the revolution that we had in the recent years with the computing power, which enables that. And in fact, he also talks within another contribution that he did with Beaver, also on the fact that we should be able also, based on the fact that when we start building models which are distributed, we should also reconsider the way how communication is made. Today, communication is all about moving data from one point to another point. However, when you embed devices with computing and data storage capability, you don't want to move data anymore from one point to the other point. You want to move what you have learned from one point to the other point. And what you have learned from one point to the other point is the construction of this model and what you exchange in a network. And this is what we're trying to build here with the 6G realm, is not anymore the transfer of data from one point to the other point, but the transfer of models which starts to get aggregated and build up this collective intelligence from this massive individual intelligence. Now I'm going to show you what we've been doing these last years to work on these two aspects. The first is AI for networks, which I think is the classical realm of you have data and you start building data-driven approaches to improve the performance of systems based on the fact that the models that you have are insufficient in terms of representing what's happening. On the other part, I'll talk on the part which is more challenging, is building exactly the network which enables this connectivity of the different models. And the experience I had, I'll go very fast on it because I don't think I have much time. And one of the reasons I came up in working more intensively on applying AI for networks is an experience that I had in working a couple of years ago in my former company on improving what we call the voice over LT experience in a 4G network. So these are acronyms that you may not understand, but classically what it means that in a 4G network, which is mobile for internet, it has not been designed for calls. It has been designed for voice over IP because everything is in internet. So in general, when you make a call on a 4G network, the quality of your call is very bad compared to a 2G phone, for which voice has been built on a 2G system as a technology, whereas in a 4G system it has been built up as an application. And we've been working many years on trying to improve basically the quality of a voice call on a 4G system. It has been extremely hard because when you look at internet, it's not just about how far you are from the access point where you have a very good SNR, but it's also related to where the servers are, the whole protocol. You have what we call an end-to-end problem, which is extremely complicated to represent. I've been working many years on trying to find models which could be sufficiently representable of a voice over LTE or voice over IP communication link, and it never worked because it's extremely complicated. The day we understood in our community that data-driven approaches could enable us to improve the system, where we had a lot of data coverage, performance related to a lot of layouts of access points, which are your Wi-Fi access point, things have changed. And here, this is a typical example we've been working in the recent years, showcasing the improvement that you can have on voice quality related to calls that you make on a 4G network, with downlink improvements of 81% and uplink performance of equivalent kind of percentage. And today you have to know the whole industry has been looking at how to relook at the problem of performance and improvement of the system, not anymore from basically a classical optimization perspective where you look at wireless algorithms, where you look at AI algorithms, where the value goes from the link, which was previously to the data, and where instead of tuning your parameters manually, you set the target goal. And here you have a set of examples just to show you the kind of techniques that we're using today in terms of the improvements of our system. It goes from things which are, for people who are familiar with that, very physical layer, in the sense that you're talking about exactly bits, to things which are more at upper layers in your system, which are basically video streaming and stuff like that. And as you can see, the kind of algorithms go from regression, clustering, classification to things which are related to deep learning, reinforcement deep learning, transfer learning, and graphical algorithms. Transfer learning, for example, is extremely important for us in the sense that when we start designing a system of a network which operates, for example, in Paris, then we don't need to relearn all the configuration of the parameters of a network when we deploy it basically in London, because there's a lot of similarities in how the users behave in Paris and in London. We need to tune a bit with the new data that we're having with the users that we're having in London, but basically we start scratching the initialization of our neural network exactly on the optimal parameters that we found in Paris. And here you have also a couple of examples, which I will not dig in, on which basically, again, in terms of optimization, things are being used on how you can beam your signal in terms of transmission, in which usually what you do, you try to go to the signal processing community, where you try to learn basically the kind of channel propagation and find exactly how to do the precoder to your transmission. In the realm today, what we do is that to find the beam, well, we have a set of transmission systems with antennas, which beam for different user positions in space. And whenever there's a new user in position in space, then we interpolate using these machine learning algorithms to find what is the optimal beam without a full understanding of what are the frequencies we're using and all the settings that we're talking about. Same thing for techniques like localization. Localization, for example, is a technique which are based on fingerprinting, where basically whenever you have a position, you have what we call a spatial response. It's a spatial electromagnetic response, which is sent to your access point. And usually what you do is that you have a set of data where you have basically different positions of a user in space and different signature, which are these spatial electromagnetic signatures. And what you do basically is whenever you have a new spatial signature, well, you can infer basically on the position of the users by again using these machine classification methods to do that. And again, a couple of other techniques, if you're interested in that, related to scheduling, also resource allocation, where we use multi-agent reinforcement learning. Because whenever you want to transmit, as I told you at the beginning, well, in general, you transmit towards what we call your access point, or your computer transmits to your access point. In general, you don't know at which rate you transmit, because basically the environment that you're having maybe is not good, and so you lose a packet. Whenever you lose a packet, the receiver sends you back the information saying, oh, I do not acknowledge the receiver in terms of what I received. And so you lower basically your low rate and you start doing that. On a point-to-point setting, this is quite easy to solve. However, when you have multiple users, the whole process within the realm of multi-agent deep reinforcement learning that we've been using to be able to optimize its performance. And then in terms of understanding these kind of systems, we're still stuck at this moment for information. And we're trying to look at what we call the large system limit and looking at approaches related to mean field multi-agent deep reinforcement learning. Now I'm going to talk about the part which I think is the most important for all of us here. And that is related to what we call networks for AI. Today, the way we build networks is very easy. We have devices, they gather the data, and then basically whenever you want to have some kind of model which is built, all the devices sends that to a central, basically, cluster, which is in general the base station. The base station aggregates data, then basically process it, and then a model is inferred, and then it's sent back to the user. This is something that is not possible anymore. Many reasons. One of the first reasons is the latency. We're talking about 5G systems in which we're talking about 1 millisecond latency. Second is, of course, all the privacy issues which are incurred by that. And the third one is, of course, the problem of overloading the network with a lot of data, which is coming back and forth, whereas at the end, you only want the result. So the big question today in the community of what I call here mobile AI is to come basically with a unified training and inference network, which can play between the device, the cloud, and the edge, and where basically you start standardizing the interfaces and how these systems are going to talk, how often they're going to talk, what kind of exchanges they're going to do. Are they just going to exchange the weights? Are they going to exchange some things like that? The type of frameworks that are being built today are mostly cloud-based, in the sense that you cannot take into account the kind of computing power, the kind of energy consumption that you have at the edge. And this is posing a lot of problem today. It's posing even more problem that devices now are being shipped to the market to do that. And of course, the question is that we're having a plethora of devices which are on the market today, and in which we need to build this kind of communication system that enables these things. And we need to build also the kind of algorithms which enable that. Of course, one approach to do that today is related to all the federated learning approach, where each device basically on its own learns with a small amount of data it has, trains the neural network, and then it exchanges with the other devices, basically the weights and the number of layers, by creating an aggregated model. And then basically there's some kind of broadcast of that information, and it's updated around that. Second difficulty also that we're having is how you start building neural networks which work at the device level. Doing that is also a big difficulty because you need to lower your precision of your AI. What we mean by lowering the precision, it means that by going into what we call something like a fixed point with a certain resolution, you go to weights which can only take values which are 0 and 1, for example. And when you take values which are 0 and 1, you start building what we call binary neural networks. And if you start building what we call low precision AI, then the question of designing neural networks becomes complicated, because at the heart of the network is a process called training, as you all know. And training on which you fix the weights to take only certain values, it turns out to be extremely difficult, because as you all know, by training, you do optimization. Optimization is a derivative. A derivative is a gradient, and this is at the heart of all these gradient descent systems. However, once you have weights who have a low resolution, it becomes basically a problem of optimization, which is combinatorial. And then you need to use techniques related to decoding, for example, on which, as you know, maximum likelihood cannot work in all the heuristics, and becomes a very challenging issue on understanding what kind of precision you can go in terms of building your neural network when you're fixing a bit the complexity in terms of precision and what you're doing. And this, of course, imposes also a lot of new challenges also on how you build the network. As of today, I'm giving you the current way people are doing it. They're keeping the current network as it is and saying, okay, what I'll do is pick up all the data that I'm accessing in every point and then sending it to the cloud, and having a centralized AI server, which will crash that data and then do some predictions which are related to the problems I showed you before, typically how I can localize a bike, for example, and then building the model for localization of a bike, and being able then to pour that and being inferring the parameter. I give you the example that this shift is going on today, where AI is at the terminal site, is at the site, at the edge of the cloud, meaning when you have base station, when you have devices, when you have your servers, and very far away from the servers. And of course, the kind of exchanges that you need to do and how often you need to do, and what is the kind of distributed type of algorithms is a big question. Of course, you can basically just say that I'm going to do a pervasive network in which I put AI everywhere and start building some just exchanging of parameters which are related to what I said before. But rapidly, you realize that these kind of systems do not scale. What I mean, they do not scale, meaning when you have a huge amount of devices, if you start doing a round-robin exchange basically of the weights, then it will take you a lot of time before you take a decision on what you have to do or constructing your model. And as you know, in our networks, time is limited. We are talking about mobile networks, meaning that the configuration of your system changes continuously, and in which basically you need to find at each moment how to change the configuration of your system. This is on top also on the notion also of how you communicate between two intelligent devices. As I told you at the beginning, the notion of semantic communication came in quite rapidly within the work of Shannon. And this is also at the heart of the work that our community is doing today in trying to define the notion of semantic communication through this process of having embedded computing power and storage, and how basically what you want to build when two devices communicate is not exchanging data anymore, but building what we call a common understanding. That's your goal. Whenever you have two devices which communicate and have the ability to store the past, well, the more you communicate, the less you need to communicate after, because you build a model and you can build what we call a common understanding. The notion of semantic information, the notion of this common understanding is at the heart of the work which is being built today by the Communication Society by using basically leveraging from all these AI techniques that we're talking about. I think I gave you a rough overview with the time I had of basically the application of AI in the telecommunication industry and the challenge and opportunities that you have over there. And of course, I'm quite happy to respond or answer some questions either now or by email.
Thank you very much, Professor Debbah. Good to hear your talk, which is really related to with a mobile network, which is used by everybody every day, you know, so it's great to see the application there. Okay, so now I'm going to be the last person to present. So between you, your good evening, and the summit, so I'm the barrier between these two. Okay, could you just unload your presentation? Yeah. Okay. All right.